All right, welcome to topic 9.10. In this topic, we are going to be looking at molar volume and gas stoichiometry. So we're going to go back to a few things that we've seen before and build upon them through the lens of volume and behavior of gases. So a couple of things that you will find useful. Periodic table will be good. Your formula sheet will be useful as well. And you may also want to find your mole map from our last unit because we have most of the information filled in, but we have a little bit to add in. So what we're looking at here is applying a new constant called molar volume. So there's a couple of things. We know that no matter what gas it is, it could be something like helium, which is monoatomic, it could be nitrogen or oxygen, which is diatomic, or it could even be nitrogen dioxide or carbon dioxide, which are compounds. What we see taking place is that if they are at STP conditions, STP means standard temperature and pressure. We find that they all occupy at 0 degrees Celsius and 1 atmosphere 22.4 liters. So this is known as molar volume and is a constant that's used very similar like Avogadro's constant. So what we have is this last piece of our mole conversions is that if you want to go from the mole to STP conditions, volume of a gas, which is liters, we use that 22.4 liters over 1 mole. Okay, again, this is a constant. The opposite direction, 1 mole would be the numerator and 22.4 liters would be the denominator. Just as another refresh for our conversions, if you recall, mass is grams, and we use molar mass as those conversion factors. And then here, representative particles can be like atoms and molecules, for example. We use Avogadro's constant. So hopefully you have these two parts filled in from previous topics, okay? So this part should be all that you need to add. So we're going to dive right in. And in this first set of examples, it says that we're going to go ahead and skip number 2 and our number 1 and start with number 2. When we take a look at it, it says how many grams of carbon dioxide. So we know that we're solving for grams. And it says here are in 1 liter balloon at STP. So the STP just tells me that molar volume is held true because it's being held at 0 degrees Celsius and 273 Kelvin. Okay, so for my setup here, I'm going to go ahead and take my 1 liter, and I'm also going to include that this is 1 liter of carbon dioxide, CO2. We are changing this from liters to grams. And so again, your mole map helps provide a visual on how to go about setting this up. We're starting here at liters and we want to get to grams. So to do that, the middleman, like before in our last unit, is we have to go through the mole and we use molar volume to get there. All right. So when I go ahead and start setting up my problem, I then put 22.4 in my denominator in order to make those cancel, and that's equivalent to 1 mole. So again, where we're at is our central point. To get from moles to mass, we need molar mass. All right. So carbon dioxide, CO2, we have 32 for the 2 oxygens and 12.01 for carbon. And so 44.01 grams is to 1 mole. So again, keeping track of things that we've done all along, liters is canceling here and moles is canceling. That takes me to grams, which is what the problem asked us to find. And so all I need to do is run this through to get my final answer. So I'm going to go ahead and take my 1 and divide that by 22.4 and then multiply that out by 44.01. And we get 1.96. I can keep 2 sig figs, so I do have some rounding here. So that 6 rounds up the 9. So in order to make this truly have 2 sig figs, we're going to say 2.0. And now I'm at grams of CO2. All right. So in this next example, we have 1.2 times 10 to the 24th molecules of nitrogen at STP. How many liters does this contain? So when looking at this problem here, you have to recognize that we, again, are given molecules. And more specifically, it's molecules of nitrogen. What it's asking us to find here is liters.
Sorry, you're.
Oh, 1 second.
Can I steal a paper clip? Oh, no, normal size.
The container up there in the front there's a ceramic jar up there by the color trays.
Thank you.
Okay, sorry for the pause there. So how many liters does it contain? Okay, so what we have is our given of 1.2 times 10 to the 24th. And that's MQL of nitrogen. Okay, what we're trying to figure out is liters. So we're starting on this part of our mole map, and we have to get to moles through the use of Avogadro's constant. I need to divide by Avogadro's constant. So 1 mole is to 6.022 times 10 to the 23rd MQLs. But we're not done because the problem asks for liters. So to get from moles to liters, I go through molar volume, my other constant. 1 mole is the denominator, and 22.4 liters is my numerator. So in order to solve, we're going to take our constant, our given, not constant, but 1.20 to the 24th, divide that by Avogadro's constant. I'm not going to worry about rounding at this point. I'm going to multiply by my 22.4. And again, my given, taking a look at the setup here, has 3 sig figs. I can keep 3, so 44.6. The last thing is molecules cancel, moles cancel. My unit is liters. Okay. The other thing we covered today was the idea of stoichiometry and how we can tie in volume to a stoichiometric relationship. Well, one of the founding pieces of a stoichiometric relationship is a balanced equation. Ideally, you should hopefully recognize this as a combustion, and combustion reactions need to be balanced in a certain order, starting with carbon. I have 3 carbons on the reactant side. I need to get 3 carbons on the product side. A coefficient 3 will take care of that. You should balance hydrogen next. There's 8 here. So to get 8 on the product side, I need a 4 in front of my water. 3 times 2 plus 4 times 1, grand total of 10. I'm going to put a 5 here to get 10 total oxygen. Okay, so again, like up above, we have a given. And so I have 0.350 liters of propane. Propane is a C3H8. Okay. What it wants us to solve is what will the volume be in liters of oxygen. Okay. So with stoichiometry, if you recall, it kind of has 2 sides to it. We have a unit of what we are starting with. So we're starting with liters of C3H8. We want to figure out what is that equivalent to in liters of oxygen. Okay. So I'm going to show you the long way and then give you the shortcut for solving this style problem. Okay. The long way is to use, again, our information from our mole map. How we get rid of liters is through molar volume. 22.4 liters is to 1 mole. Okay. Well, that is going to help me start working towards solving for oxygen. So I need to swap it from my reactant propane to my reactant oxygen, much like the grilled cheese, slices of bread, cheese situation from earlier in the semester. We get our mole ratio through our balanced equation. This is a 1 to 5 ratio. So 1 mole of propane is my denominator, and 5 moles of oxygen is my numerator. The last step is I have oxygen, so I took care of that, but I don't have it in liters. So to do that, I use 22.4 liters is to 1 mole. Okay. This, you'll notice, cancels with this, and there's a very good reason for that. If you take a look at our subscripts, propane has a G there for gas, and oxygen has a G there for gas. We are going from liters of a gas to liters of a other reactant, which is also in the gaseous state. So there's a much easier and shorter way. This mole ratio is what we're going to keep. but it's no longer going to be a mole ratio. So I'm going to go ahead and rewrite this. I keep setting things down. There we go. I'm going to take my given of 0.350. And the much shorter way is to use a volume ratio, liter ratio. So instead of saying 5 moles of oxygen, we're going to say 5 liters of oxygen is to 1 liter of C3H8. This works. This can be done in one step because we're starting with the volume of a gas, because we are ending with a volume of gas. So again, if it's a liter to liter, gas to gas, we can do this in one step. That's not all the time, and I'll show you what to do here in a second if we can't. So when we multiply and we can keep 3 sig figs, we should get 1.75 liters of oxygen. Okay? So in the last couple of examples, on the back side or the second page of the notes is something that changes things up a little bit. So quicklime, CaO, is produced from the decomposition of calcium carbonate. Okay, so the idea is if you look, calcium is balanced, carbon is balanced, and if you total correctly, this is 3 oxygen, so your oxygen are balanced. These are the ones we like. So I'm going to go ahead and write in a 1 just so we know that, yes, that's a balanced equation. Looking at the given, we have 125 grams of calcium carbonate. We want to solve for volume of carbon dioxide, volume being liters. Okay, so this is different in that in this previous example, we went from liters and ended at liters. That is why we could do it in one step. Here, we're not starting with liters, so it doesn't work that way. We have to get rid of grams. Okay, so I go ahead and write out my given of 152 grams. You always have to get these to moles. If this is calcium carbonate, CaCO3, we need to convert that to moles through the use of its molar mass. If we add up 3 oxygen, a carbon, and a calcium, we should get 100.09 grams per 1 mole of calcium carbonate. That allows grams to cancel. Okay? Here, we're going to swap out what we're describing. We're going to switch from talking about calcium carbonate and show the ratio between calcium carbonate and CO2. It's a 1-to-1 ratio. But because this is a solid and this is a gas, I can't use liters. I have to use moles. You can only use the liter to liter ratio when they are both gases. So 1 mole of CaCO3 is to 1 mole of CO2 because we're solving for carbon dioxide. Okay. The last step here is we want to find volume of carbon dioxide. So I need to cancel out moles of CO2. And how in the world do I get liters? The only thing that helps me with that is molar volume, the constant 22.4 liters. Okay. Then we just got to crunch our numbers. So we're going to take 152 divided by 100.09 and times by 22.4. I can keep 3 sig figs, so 34.0 is my answer, and my unit is going to be liters. So 34.0 liters of CO2. I'm going to go ahead and work out this last one because I know these last couple examples are where students have the most problems. Okay, so in this last one, sodium reacts with chlorine to make sodium chloride. Looking at it, it's not balanced. I'm going to start by balancing my chlorine and then balance my sodium, and I then have a balanced equation. Okay, my given in this situation is 4.81 grams of sodium metal. Okay, so if you look at sodium and it says the word metal, that tells me at room temperature sodium is a solid. Okay, so unlike the first example, my shortcut isn't going to work. So this is grams of sodium. So the only thing I can do with grams of sodium is convert it to moles through molar mass. If we look at our periodic table, sodium is not Hoffman-Kleiber, it's just 22.99. Okay? Following kind of the suit with up above, you then move into your mole ratio. Okay? We swap from talking about sodium, which the coefficient here is 2 moles of sodium. And then if I read through the problem, we want to figure out the volume, meaning liters of chlorine. This ratio is a 1-to-2 ratio. For every 1 mole of chlorine, you need 2 moles of salt or sodium to make the salt. So lastly, Looking at units, my grams have canceled, my moles of sodium have canceled. It wants it in the specific unit of volume. So 22.4 liters is to 1 mole. So I take my 4.81, divide it by my 22.99 to convert it to moles, divided by 2 to change it to moles of chlorine, and multiply by 22.4 to then describe that as liters. I have 3 sig figs to start, so 2.34 is going to be my answer here. And that's liters of chlorine gas. And that's it for topic 9.10.